Chapter 11 is the nonparametric analog of Chapter 6, which is about two-sample variance tests and ANOVA. So in Part A, we're going to do squared ranks, which is the two-sample variance test. Okay, so we have two samples that might be from different distributions. And what we want to know is, are their variances the same or not? Okay, so how do we do that? First, convert each y and x into its absolute deviation from the sample average. Okay, so what I mean by that is take the yi's minus the y bars, absolute value, and do that for I equals 1 up to ny. And then do the same thing for the x's. J, oops, let's be consistent with calling that j. And call those, I'm just going to, for notational convenience, give those letters VI and UJ. Okay. Then assign ranks in the usual way to the combined sample of U's and V's. So I've got V1 up to V and Y, and then U1 up to U and X, and that's going to give me some ranks that I could call R1 V up to R and Y V, and then R1 U up to R and X U. Okay, I'll show you exactly how to do that in code in a moment. Using those ranks, there are several common test statistics. There's more in the book, but I'm just going to show you one. As you might imagine, you square the ranks. So you take the ranks from the Y group, or the V ranks, and sum them up, or sum up their squares. Okay, and you could call that R bar squared V, or I'm just going to call it R bar squared. Okay, let me show you in R. So here's an example where I have two samples. One of them, the Y1, is the number of bicycles on several Green Line metro trains in the Washington, D.C. metro area. And the X1s are counts of bicycles on Orange Line trains. Okay, so those are the two samples. Let's extract their dimensions. So ny is length of y, and nx is length of x. Okay, and then we'll calculate their absolute deviations from the sample average. So we'll call them y1v, abs of y minus mean of y, and then u is abs x minus mean of x. Okay, then I can rank the combined sample of U's and V's. So I'll call that RUV, or VU. Rank the combined sample of V's and U's. And then I can calculate the test statistic. So first I'll extract out the part that has to do with V. So that's RUV, or VU, 1 to ny, because the statistic only involves those. those, and then my R2 bar is 1 to ny, 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 1 whoops, I'm struggling a little bit here. R2 bar sum of the squares of the V ranks. Okay, so that number is 1,390, and that number is totally meaningless without understanding the sampling distribution under the null hypothesis of equal variance. We will use that equal variance is a special case of having the same distribution, which means that we can just randomly permute n ranks. So we have n, which is nx plus ny, simulating from the null distribution. So I can just sample 1 to n ranks. So just shuffle those ranks. Then I can sum up the squares with the first group. So let's make a big simulation the usual way for I in 1 to capital N. R2 bars, rep, NA, capital N. So these are my samples. So these are my virtual RVUs. And then I'm going to extract RVs from that, which will be the first NY of them. And then my R2 bars are the sum of the squares of those ranks. That should do it. So this is just like in chapter 9, where I'm creating random ranks and looking at the ranks from the first group, but now I'm summing the squares of those so I can get a statistic like the one that I've calculated from the data. Okay, so I should be able to run that. Visualization. Oops, our 2 bars. There we go. AB line V equals R2 bar, call equals 2. I don't think I'm going to be able to reject that null hypothesis. Oh, you can't see it. Let me show you. Okay, so there's the visual. I don't think I'm going to be able to reject that null hypothesis, but I can calculate a p-value as 2 times mean of R2 bars less than R2 bar. 12%. So I'm not going to be able to fail to reject the null hypothesis and conclude that the 2 samples have the same variance. Okay. So how do we do it the math way? So sampling distribution easy by simulation, but harder, still doable, by math. How? Well, I'm going to punt a little bit. I'm going to tell you to see Appendix B3 in the book. This involves solving a subset sum problem, just like the chapter 9 calculations. In fact, I've got the full code for this and we're going to use it in a moment. So a CDF is provided as PSQ ranks in ranks.r on the book webpage. So if you've got the ranks.r file downloaded, you can load it in just like this. So the math way, you have to source ranks.r. Be careful when you download ranks.r, you've got to make sure it's in the same directory as your code file and that your working directory is the same as the code file. So I can load that in, and then I can do 2 times PSQ ranks R2 bar, and then give it the dimensions of the sample, and it will go off and do some calculations. And you can see that's pretty darn close. 0.1199 is pretty close to 0.1206. So that is the squared ranks test.